Okay, a couple of examples for inductance. The first one, we want to find the inductance of a coil, just a single coil, not a single loop, but a coil. If it produces a change, we don't know how many loops there are, it doesn't matter for this calculation. Moving on, produces an EMF of 2.5 volts when the current changes from that to that in that amount of time. So we're going to use our equation for the EMF related to the inductance, so L times di dt, and we've got the EMF, so we can go ahead and plug that in, 2.5. The inductance is what we're trying to solve for, so that's L. Now in this case we just have initial and final values, so we're not going to have instantaneous, but essentially we can plug in delta I over delta t, so that is going to be our final I, which is 25, minus our initial I, so minus a negative is going to give us a positive 28 milliamps. I'll just put a milli out here to remind myself to multiply times 10 to the negative third. And then I'll divide that by the delta t, which is going to be 12 milliseconds. So my millis will actually cancel. And I do a little bit of quick algebra, and I can solve for the inductance, and I get 0.566 henries. So nice, quick, easy calculation there. This next one is a little longer. Alright, here we want to find the mutual inductance between a long straight wire and just a single loop hanging out near the wire. So we'll start out by saying the mutual inductance, we'll find it in terms of the mutual inductance on this loop essentially. So we're going to say N2 times theta. I'm going to call this guy 2 and this guy 1. Not theta, phi, 2, 1 over I1. Okay, now I can say that there's a single loop, so N2 is equal to 1, so I just have my flux over my current, and that flux in this case I actually need to use an integral because my magnetic field is not going to be constant throughout here, so I'm going to have 1 over I1, and that flux will be the integral of b dot dA, and b1 dot dA, this dA2 if we want to keep all of these subscripts here. Now we know what the magnetic field from a wire is, right? We've got b1, which is going to be mu naught I1 over 2 pi r, and then the area of this loop, we're going to say that dA is going to be the width of the loop, W here, times dr, so we can integrate across that. So if we plug all of this into our integral, everything in this b expression is constant except for that r, so I'm going to pull all that, the rest of that junk out front. So I've got a mu naught, did I call that I2? It should have been I1, sorry about that. Mu naught I1 over 2 pi, and then I've got another I1 here, this guy here that was here before, so those actually go away, which is good news. And then we're going to have the integral. I've got the r in the denominator there, so 1 over r. I'm going to plug in w times dr. That w is constant, so I can throw that out in front here, and I've got dr. My limits of integration are going to be from L1 to L2, going from there to there. So this works out to be mu naught w over 2 pi. The integral of 1 over r is going to be the natural log of, well, I'll just call it x, and then plug in my limits. I guess I should have used a dummy variable like r primes or something, and then this would have been ln of r. But okay, so from L1 to L2, and so that gives us this expression here, pi, where we're going to have ln of L2 minus ln of L1. I kind of combined my L in there, and that should be a 1, having a hard time. Okay, and when you subtract natural logs, you can combine those and divide them, so our final expression for the mutual inductance in this case is going to be this nice, neat, tidy expression in terms of these distances here. Okay, that's all. We will see you next time.